This talk is on memory leaks, which is something that we all think that we should know about, but might not actually be handling in practice. So by way of introduction to me, I'm Elizabeth. This is a graph of my confidence in Android development over time. So I started out on the far left there with a degree not in computer science, but in biomedical engineering, which is basically a degree in everything with a math major. And then out of school, I started a few companies that had something to do with technology, and one of them dealt with digital health. So I started learning how to cobble together apps, and I published a few. I had a few prototypes out, and I felt like I was on the top of the world as an Android developer. I was being really productive, all my apps were out, my users were clinicians, so they're not happy no matter what. But I had some apps published, and I thought, wow, this is a great time for me to take this show on the road and join an Android development agency, which is when I joined this one, who is also my sponsor, Possible Mobile. So thanks to them for letting me speak today. But I joined an agency, and I was put on a large team of Android developers, and for the first time in the history of my code writing career, my code was peer reviewed. And I quickly realized that I wasn't quite as good at Android as I thought I was. And one of the huge knowledge gaps that I had was related to Android memory. So some of my PR feedback was like, you are attaching a lifecycle to a view holder. What's going on here? Or you're listening to something and then you're never unsubscribing. This is a memory leak. So as a result of those types of feedback, I submitted a conference talk. And what I present today is what I've learned between the submission of this talk and today. So please bear with me. When I started watching videos, I had really a lot of trouble contextualizing what piece of memory was being presented to me. So I thought it might be useful to walk through Android memory in a holistic way. And I'll just quickly talk through this slide, but we'll go into depth more in the first part of the presentation. And the second part of the presentation, we'll just do some live coding and have fun. So how your phone manages memory is in terms of zeros and ones, and you have brilliant manufacturers who have created chips so that we don't have to worry about explicitly the zeros and ones. And then the Linux kernel sits on top of your phone and provides abstractions on top of those zeros and ones. This will allow you to allocate memory, provide you with a contiguous virtual memory space, and paging and processes on which you can actually be productive. On top of the Linux kernel, the Android team developed a runtime which allows us to write Java code and be productive in Android. And there are also native libraries that can take advantage of the Linux kernel's dealing with memory, but also have to allocate their own memory using the C or C++ language. And then finally, at the top of this stack is you and the Android framework. So written in Java or Kotlin, you have your objects and your primitives, and a lot of the memory is managed for you, which is great. And sometimes it's not quite managed correctly, which is when you have a memory leak. So we'll get there. Let's start at the phone. I'm not going to go too deep into the zeros and ones of things, even though I find it incredibly interesting. But I don't want to bore you with things that you'll really never have to worry about. I pulled down the Pixel 3a spec sheet, and you can see we have something called RAM and something called storage. Your storage is where your persistent storage goes, your apps are stored, and if you have anything that's stored in a database, this is where it ends up. But what we're really interested over the course of this talk is the RAM. And it's important to note that we've been on a very strong upward trend in the RAM specs that are available, even in entry-level phones. I mean, just a few years ago, we had devices with 512 megabytes of RAM, and now we're looking at this affordable phone with 4 gigabytes of RAM to start out with. So memory and how we deal with it is evolving rapidly over time as the device manufacturers are making more and more of it available to us, which is pretty sweet. On top of your phone, So now out of zeros and ones land, I want to go over how we can treat RAM as programmers. And generally we partition RAM into two types of memory. We have either stack memory or heap memory. So your stack memory is really a scratch space that's sort of provided to us where we can allocate objects in a last in, first out manner. So if I want to allocate this new pink object, it's pretty obvious where I'm going to put it, right on top of the rest of the stack. And then if I had to throw that, reference that object later, I could pop it off the top of the stack. So you can imagine the bookkeeping here is really simple. And this is really only used for function, local, and variables that have a discrete amount of space that they take up, so your primitives. Your heap memory is your larger free-floating memory. And I've represented this with a fragmentation element. So your memory in a heap could be living anywhere, since you need to allocate your large objects at any given time. And you may not have space for them so that you can have a nice contiguous heap allocation. So this object in order to allocate this object on the heap, we would walk the heap until we find a space that's large enough and put it in there. So you can imagine the bookkeeping behind the heap is a little bit more complex. And most of this talk will cover concepts that deal with heap memory, because this is where our objects go, and this is where we can get in real trouble with memory leaks. So our Linux kernel, written on top of the phone, mediates our access to system and components, including RAM. And the Linux kernel manages memory, and the basic unit of memory that it manages is pages. So this is your 2 kilobyte to 4 kilobyte, depending on the device, unit of memory. That's all those capacitors down on the RAM chip. And a page of virtual memory can either be used, cached, or free. So a used page is one that's in use by the program. We're writing to it. It has some data. A cached page is a page that has some data and could also be backed by internal storage memory. And then free memory is memory that's ready for us to write to. So the Linux kernel on Android does a couple of special things when we get into memory pressure. So this kind of weird graph that I've drawn, on the far left there, we have a comfortable memory situation where the memory demand, the memory supply can meet the demand. We have enough free pages where if a system or a process asks for more memory, we can give it to them without worrying too much. When we get into more of a memory pressure situation, Linux kernel has a couple of tools in its belt to manage those. So the first tool that it uses is called swapping. That's why I set up with the used versus cached pages. Swapping can take a page of memory and either write it to a disk, or on devices later than Lollipop, I think, it can write it to ZRAM, which is just also RAM space but compressed. So it's called swapping because we're moving between RAM and another type of storage or another compression level of storage. You're also swapping, you're also trading off between a very fast access and an access that's going to require either some disk I/O or some computation to read that ZRAM. So if we start swapping pages and we're still requesting more and more memory, and we get into sort of a critical position where we have very few pages that are able to be cached, what the Linux system can do for Android is it can kill your processes. So that's low memory killer, and that's why you see a spike in free memory. Each process has some attached metadata to it, which will tell us when it was created and maybe its priority level. So you can think that the wallpaper might have a high priority level on your phone because the user experience, if you were to enter your phone and not see wallpaper, would be pretty dreadful. So Linux will kill a random process, or not a very non-random process, for you based on its priority level. And then the situation that both of these processes are trying to avoid is direct reclaim, which is when we're completely out of memory and we need to allocate a new page. the Linux kernel will have to either flush out a dirty cache page, which means write something to disk or to ZRAM that has been updated since its last write, or it'll just have to kill pages. So thank God the Linux kernel is there. It does a lot for us. And now, for the most part, we don't have to worry about it. So on top of the Linux kernel, we can trust that we're going to be able to allocate and deallocate code, allocate and deallocate objects with relative ease. For native code developers, this means that we're going to use C or C++ to manually declare those allocations and deallocations. But we're Android developers, and we really want to use Kotlin and Java. So the runtime is what enables us to actually run our Kotlin or Java on the kernel as a process. So the runtime process takes in a specific file format called dex, which is specifically a compiled version of Java code specific to Android. And the runtime also allows us to start processes and share some memory across processes by providing a zygote, which spins up a new virtual machine every time we want to start an app or a service. So let's talk a little bit about how the Android runtime has decided to save programmers from the huge job of actually manually allocating and deallocating their objects. And I think it's helpful to think about this by looking at how Apple and Android manage their memory. So on iOS, we have a system called automatic reference counting that's available for Swift and Objective-C. So it's easy as 1, 2, 3, I guess. In step 1, we have the square object that's holding a reference to the circle object. So the circle object has a reference count that's associated with it, and that reference count is 1. Step 2, if we remove the square object, then the reference count for that circle object is now 0, and immediately and deterministically, that object is deallocated. So that seems pretty simple. In the Android strategy for the same situation, we have garbage collection. So we're not necessarily counting references. We might set some marks on some objects, and I'll go into that later. But just to play out the same scenario, so we have our square that has a reference to our circle. We take the square away, and then the circle's kind of still there. And then after a possibly indeterminate amount of time, that circle is going to be collected. And I promise it's going to be collected, but we have a less deterministic system. So let's look at that, what that actually does. And the algorithm that Android uses for garbage collection is called mark and sweep. So this diagram is showing us a graph of our objects. Certain objects are going to be labeled as garbage collection routes. So in order to determine whether an object is connected to the system, we're going to start by traversing the tree of all objects starting at the garbage collection route. So what the garbage collector does is in a first phase, it goes through and it marks all of the reachable objects. So there's a mark bit on each object. I've marked in pink each object that is reachable by traversing starting from the GC route. So we have some objects on the left part of the screen that didn't make the cut. That's sad. Those objects are called garbage. And then in the sweep portion of the algorithm, we're going to traverse the heap. This time we'll look at all objects, decide whether the object we'll look at the marked bit of the object, and if the marked bit is 0, that's our garbage. We'll take it away. We'll reset all the other objects to 0, and we've swept. A key consideration, so this seems more complex than the iOS way of handling automatic reference counting, but one advantage that we have is if you look at this garbage, the garbage with an arrow pointing to each piece of garbage, In Swift, that's called a retain cycle. And in order to have that collected, the programmer has to specify what type of reference the object has to each other. So one of those objects has to say like, oh, I don't really care as much about this object as it cares about me. It's called a weak reference, so that Swift can go and clean up that garbage. So mark and sweep, garbage collector is what the Android runtime team provides us, and I think also what the JVM does if you write Java for another framework. So a couple of fine points that the Android runtime team has provided to decorate this concurrent mark and sweep implementation. We have compacting garbage collection as of Android L. So when you have objects that are being allocated and deallocated over time, you're going to get a fragmentation of the heap based on where you can allocate your objects at any given time. And what the compacting garbage collection can do is just move everything so that it's in a contiguous memory space, which is really nice. Also, as of Android L, we have generational garbage collection and a large object heap. So we've separated out some particular spaces of the heap for particular types of allocations. For generational garbage collection, we theorize, and I'm sure it's been proven, that objects that we create in the short term are likely to be collected in the short term. So if you have an object that's newly created, it's more likely that we're going to want to garbage collect that item soon as opposed to an object that's been around for a long time. So we'll actually do more frequent garbage collections on objects that are newer as opposed to objects that are older. For the large object heap, this applies to bitmaps and a couple of other types of objects that can be really large. Instead of doing something where we try to traverse the heap and find a space to fit it in a heap that may or may not be fragmented, we're just going to declare an entirely separate space where we can put those objects. And so our allocation time for larger objects is near instant, which is great. And then as of Android O, we have concurrent garbage collection. So this sort of combines the idea of compacting garbage collection with the strength of running it every garbage collection cycle. So imagine if you're always compacting your heap and always compacting your heap, then every time you try to allocate a new object, you actually have a very easy decision to make, and you don't have to traverse the whole heap to find where you want to allocate your object. So we have something called a thread local bump pointer allocation. For each thread, we have a different heap, and for that heap, we can do extremely fast allocations because we're compacting our garbage all the time. So we're really happy that we have all of these utilities so that as a Java or a Kotlin programmer, we don't have to really deal with the nitty-gritty of allocation and deallocation. Up in the Android framework is where we can actually start to be productive on Android. And this is where we can sort of put the pedal to the metal and map some of these more abstract concepts to actual objects that we're going to use in our code. So our GC roots in Android, according to the framework, are going to be threads, static variables, singletons, which I know Stuart told us that it's fine to use, native references, and the actual classes that we're going to compile. And then the objects that we might think about as part of this heap graph or this reference tree are our activities and services, broadcast receivers, and content providers. So the building blocks provided to us by the Android framework to build Android apps. And it's important to note that these items each have a life cycle. So the Android framework team is guaranteeing that if I start an activity and then my activity is destroyed, that activity is going to be garbage collected and we will not have a memory leak unless you write it into your code. So what is this memory leak? A memory leak is just an object that we no longer need and cannot be garbage collected. So we have, it's an object that still has a reference that is no longer needed. So some symptoms of memory leaks in your code are out-of-memory errors, which is an extreme case. You'll crash your app. In general, you have a finite amount of memory that you can request from the Linux kernel. So you start with a really small heap. When you request more memory, the Linux kernel is going to grant you a larger and larger heap until you reach a limit. And at that limit, you'll get an out-of-memory exception if you try to request any more memory because you're just being ridiculous. An illegal state exception is a little bit more of a tricky one. Let's say you have a listener let's say you attach a listener to an activity or another component, and then you leak that component. If you have a callback on that component and try to do something like update a text view that no longer exists, then illegal state exception can occur. And then you also might see visual aberrations in your app that are related to garbage collections. So before Android O, there are, well, in every iteration of Android garbage collection algorithms, there are pauses where we need to lock all the threads and make sure that we're collecting garbage synchronously. But before Android O, sometimes these pauses could interfere with the 16 milliseconds in between which we need to draw frames in Android. So your UI redraws every 16 milliseconds. And if you have garbage collection events that start to surpass that time because your heap is so large and complex, then you start to see your UI react to that, and that's called jank. So after all of this abstract talking, I think we should probably dive into some examples. And we'll start with a really contrived example of a memory leak. And you can see in my sticky note what I'm going to cover here. But I think there are sort of three main ways that I can think about to leak memory, and I guess Slack maybe can think of more. But for this example, I'm going to herald a static reference to an inappropriate context. So, and by static, I mean, so static for Java just means that the object or the function is associated with your class, but not an instance of your class. So that should tell you that it could possibly outlive an instance of your class and leak an activity. So I have declared a set of contexts just to make it fun. And in my onCreate method, I have printed my heap size just for fun, so we can see what kind of memory we're working with. I've added my activity to a set of contexts. And then, just to really ramp it up, I have tried to decode a resource into a bitmap. It even took a second to load on my screen. So that's a 7.72 megabyte file that I'm just going to store inside of my activity to really associate some cost with this link. So let's run this application on a really crappy emulator because my computer's not that cool. Yikes. Anybody know how to zoom out on an Android screen? Maybe this? Oh, yeah. Okay. You guys are the best. Well, that does it. So, I have my app up, and I'm also going to open up my memory profiler. And start profiling. So I'm going to start a session that's attached to my emulator. If it doesn't crash my computer, because it's not that great, I'm going to dive into the memory. And right off the bat, I can see a trace of all the memory that my application is using. The vast majority of my application memory is attributed to native code. So for the most part, unless you're working with bitmaps, you're going to be interested in looking at the Java code that's attributed to your application. But the native code, we sort of talked about this earlier, but that code is allocated on a different segment of memory, and it's attributed to native code. So let's see what happens if I start restarting my activity. Okay, so I had a jump in memory. The Linux kernel has given me a little bit more heap to play with. I have now 274 megabytes. And I'm seeing that my steady state memory has increased. So this is a key sign that I'm doing something extremely wrong. When you create a new activity and it's the same activity, you would expect approximately the same allocation. So let's keep rotating this and see if we can get something super bad to happen. So I'm going to continue to see these jumps in memory. And you know what? At this time, I'm getting really suspicious, and I'm just going to take a heap dump and see what my allocations actually are. So it's probably really small on my screen, but you can see there's two buttons up here. At any given time when I'm tracking memory using the memory tool in Android Studio, I can dump the Java heap, and it'll tell me all of my objects and their allocations, or I can run a garbage collection manually. I wish there was a button that could help you with whatever problem you just had. So I've dumped my heap, and I'm not going to go too deep into the heap because I don't really know how to read the heap. But one thing I noticed is that I have 3 allocations of my main activity. So if I were to press on my main activity, it would jump me into an instance view where I could look into each instance of my main activity, and I could see all of the things that either reference my activity or are referenced to. So it's notable that the depth refers to the distance from a garbage collection route of that item. So you could dig through this and look for exactly what references could be causing me to hold on to my main activity. But I'm actually not going to do that because it might be a little bit easier to show you a different way. Before I show you a different way, I want to take this to the extreme and watch my heap size go up a couple more times, and eventually I'm out of memory. So it looks like at about 1 gigabyte, the Linux kernel just says no and stops giving me any more memory. And who's going to blame that? So I failed to use the memory tracking tool to traverse my heap. So I'm going to show you another thing that you can do to help interpret that heap dump for you, which is called LeakCanary, and it's a library that was originally developed by the Square team, but I think is now, I don't know, independently managed. So I'm on the alpha. It's a debug dependency, so why not? And let's just run the same thing with LeakCanary attached, and hopefully I'll stop my profiler because that's just going to kill my computer slowly. Yes, please. Okay. So let's rotate the phone a couple of times and start leaking some of that memory. So now I'm getting an icon. LeakCanary under the hood has attached a weak reference to my activity, and it's looking for when that activity is destroyed, taking a heap dump, and then making sure that that activity is actually gone from the heap dump. So when I get a notification, it means that it's found something that could be a leak. So let's go, that's probably going to crash it, but let's go into this LeakCanary notification. And resize my phone so hopefully you can read it with me. So it's telling me I have several different memory leaks reported. And when I dive into this, what LeakCanary is trying to show me is the shortest path between the item that it thinks that I've leaked and a GC root. So at the bottom, we have our activity that was leaked. And then at the top, we have, oops, not that. we have an activity which is also the GC root. And that activity has a reference to a hash set, which we've created over here, and that hash set has a reference to the leaked activity. So I want to take it back into those ugly brown diagrams that I was drawing earlier and tell you what's actually happening in a graphical way, or maybe an abbreviation of what's happening. So the GC root in this instance is a thread that has a reference to our activity, the main thread of the application provided to us by the Android runtime on a Android virtual machine spun up by the Zygote. So our thread has a reference to the activity, which then in turn references a set of contexts and this heavy bitmap. The set of contexts also has a reference to the activity. When we rotate the screen, our thread now holds a reference to a new activity, which in turn has a reference to that same static set of contexts and its own 7 megabyte jellyfish. So you can see how this might lead to a disaster. And I drew out the disaster just for fun and because I really like aquatic animals. But it's extremely easy to see how we would not want to get into this situation. So it's one thing to get us into this situation. Let's see if I can get us out. So one problem with this piece of code is that it would never exist because it's sort of contrived. But another problem is that we're saving a context that we may or may not need. So one of the takeaways from this talk might be a little bit careful with context. So one way I could fix this leak is by just referring to the application context, which is going to outlive any activity that you could create. So if I filled my hash set with application context, it would actually only have one application context because there is only one application context. And I would get rid of a memory leak. Another super contrived thing that I could do, oh yes, I even wrote out the code to it ahead of time so I don't actually have to do live coding, is I could keep a weak reference to my context in my hash set, and a weak reference would allow you to tell the garbage collector that, if I have this object and this is the only reference to the object, then we can just go ahead and garbage collect that. So great, we fixed the leak. Let's try to move on to some perhaps slightly less contrived examples. And let me pull up my sticky note so I can remember what I'm actually talking about. Oh, yes. We could leak memory very easily using either a non-static inner class or an anonymous class. So I've leaked a couple of things here. Let's look at them one by one. So in my function anonymous class leak, I have created an anonymous class using the object keyword in Kotlin. And this class is an AsyncTask that does something in the background, basically nothing but sleeping. And the reason I've chosen AsyncTask for this anonymous inner class is that it has actual costs associated with it. So you can imagine that creating an object or creating an anonymous inner class that doesn't really do anything, it could get cleaned up immediately because it's not going to take up any amount of time. So we really need to be careful when we start running tasks, spinning off RxJava observables, running threads. And Android Studio is actually telling me that this AsyncTask class should be static or leaks might occur. This is a little bit confusing until you realize that this anonymous object actually has a reference to the activity. So I can call any method on main activity from inside of this class, and it's going to hold this reference forever, whether you're updating a text view or doing anything with your activity or not. So something to look for is anonymous inner classes, anonymous classes in Kotlin. Another way you could leak is using an inner class And the same principle applies here. So I've used the inner keyword in Kotlin to spin up, this time, a thread that also runs and sleeps for 1,000 milliseconds, or a million? I don't know what that number is. So let me just prove to you that we actually have an implicit reference to our enclosing context directivity, which is a bad situation because we're going to keep this activity alive for however many milliseconds it takes for the class to run. So these are a little trickier to fix, right? So I can show you a couple of suggestions for dealing with inner classes and anonymous classes. Suggestion 1, which is my favorite suggestion, would be to cancel my task or to unregister my listener in the appropriate lifecycle of the class. So RxJava gives you disposables, AsyncTask gives you a chance to cancel it. If you have a job that you've saved from your coroutine from Kevin's talk, you can cancel that job at the end of your class. So this is a great way to manually stop that task from executing and make sure that you can garbage collect your enclosing context. And you can see that even though I still have this lent error here, I've actually taken care of the leak. Another solution, maybe just don't use an inner class if you don't need it. So in this example, I haven't actually done anything with my reference to the activity. And in Kotlin, if I just take the inner keyword away, I no longer have a reference to my enclosing context. So this is just going to refer to the thread that I've created. So one last example, maybe a slightly more fun one, because it uses the little bit of Jetpack, which everybody's into. Not quite as cool as Sunflower app, but I'll get there. So I've created a somewhat contrived view model where Kevin, don't look at this, but I've launched a coroutine into global scope that is going to update a LiveData every half second, and it's going to post a random integer to the LiveData. And so in my main activity, I have subscribed to that view model, or I've subscribed to that LiveData called random color, and I'm observing on that forever, and every time I get an update from that LiveData, I'm going to reset the background color of my application, and then I'm going to increase a counter, and let's see what's going to happen here. Absolutely nothing. Oh, okay, so we started updating the UI. Everything seems to be going smoothly because I haven't rotated the device yet. But you see what the application is supposed to do. We're slowly counting, we're changing the color a little bit. That's great. So when we rotate the application, what starts to happen is we have the same behavior. LeakCanary is telling us that something is wrong. And we're also increasing our count by 2. And then the problem is just going to get worse and worse the more we rotate the screen. So now we're jumping up by 3 each time, and so on. So what's happened here is one of the classic mistakes that I was getting shut out of my PRs for, which is observing on things forever and failing to respect the life cycle of the activity when I register an observer. So something that we would definitely want to do whenever we're looking at observing anything, whether it be a LiveData or an RxJava observable in your activity, would be to go ahead and use whatever that language gives you to either attach a lifecycle or clean up after yourself. So what's cool about LiveData is that I can just call observe and pass in a lifecycle owner. And under the hood, LiveData is removing my observer from the, it's removing my activity from the list of observers so that my activity can finally be garbage collected and I have a nice predictable behavior instead of a lot of random things firing in the background. So, to summarize the last two leaks that we sort of talked about, actually this is from the example with the AsyncTask and the thread, but it sort of applies also to the LiveData model. We have a thread that's attached to our activity, which also has references to these long-running tasks that in turn contain either an implicit reference in the example of inner thread and AsyncTask, or a very implicit reference in the case of a LiveData. And then when we rotate the device and start a new activity, we have these GC roots that are our objects and our threads that still maintain their references until those objects complete their work and are GC'd. So, I hope you've learned something interesting. I had a really good time up here trying to tell you about memory leaks. If I said anything wrong, it's because I'm still learning, and I would love for you to call me out on it in the Slack channel. If I said anything right, or you want to have a discussion about how we can all be better with memory leaks, also reach out in the Slack channel, or feel free to come and find me, and I love to talk about this sort of thing. So thank you, and thank you Possible Mobile for being my sponsor, and thank you for the conference for letting me do this.